a pleasure to talk to the SBS. Um, I'm going to explain in my talk what all these various images on the front page mean, but you might guess they have something to do with gravitational wave detections. But before we get to gravitational wave astronomy, let me, no, why isn't this working? There we go. Let me explain what gravitational waves themselves are before we get into how you use them for astronomy. So let's go back a ways to Newton's gravity, meaning going back several hundred years. In Newton's perspective, the gravitational force is pretty simple. He basically had his constant g times the product of the masses of two objects, and you divided the square of the distance between them, and you got the force, the inverse square law. And as long as the two objects were reasonably spherical, that was a good approximation. Now, that has been a very successful theory, as you know. One could do all sorts of calculations, compare observations with predictions, and until the late 1900s, late 1800s, one had excellent agreement. One little troublesome thing was that the precession of the perihelion of Mercury wasn't quite right, but otherwise it was a very successful theory, and of course NASA uses it routinely to calculate what spacecraft need to do to get from one place to another. But as successful as the theory was, it does imply something very strange. It implies instantaneous action at a distance. So for example, if the sun were to explode into two pieces, one going, say, up like that and one going down like that, according to this theory, the Earth would immediately feel the effect of that. We would no longer have a spherically symmetric mass attracting us. It would be split into two, and that would change the gravitational force a bit. This formula says that would happen instantaneously. And that doesn't make a lot of sense. Given everything else we know about the world, nothing else works instantaneously like that at a distance. And Newton knew that. I won't read this whole quote, but he basically understood that this was really pretty absurd. Didn't really make any sense at all. But being a good physicist, in fact, one of the best ever, he just swept that under the rug and just moved on to do his calculations, which is the conventional thing to do when you really don't understand anything and you don't have a clue how to solve it, but you can still make progress. So he swept it under the rug, and others afterward also tried to figure this out. And it took Einstein to figure out the resolution to this puzzle. And the resolution to the puzzle was to rethink space and time altogether. You've probably seen this kind of a depiction before. This grid, this mesh, represents a two-dimensional analog of three-dimensional space being warped by the presence of mass. In this case, we have something depicting the sun, and the Earth going around the sun is affected by this warping of space, and it's in some sense forced to go through space in what we call a geodesic in space-time. And in fact, it creates its own little warping of space, this little dimple you see here. And so that's a qualitative way to think about it. Quantitatively, it is represented by the Einstein field equations shown here. Those are famously compact and concise. There's an amusing YouTube video with Brian Greene in which he unpacks that equation and shows how ridiculously complicated it really is. Those equations are very difficult to work with, as those of you who take physics 435 already know. But nonetheless, one can derive Newtonian results in limits. I don't want to go into this kind of mathematics here, but let me just say that qualitatively, you can summarize this using the words of John Wheeler, the fellow who invented the phrase black hole. Matter tells space-time how to curve, and then curved space tells matter how to move. Now, I just described a relatively static system of the Earth going around the sun. The Earth goes around the sun at roughly 10⁻⁴ of the speed of light, and that's a pretty non-relativistic. But you can have a much more extreme system like two neutron stars, as depicted here and as depicted in my zoom background, that are going around each other much faster than that. That can be going around each other at large fractions of the speed of light. And in that situation, they're basically swirling space quite noticeably. It's not a static or slow moving disturbance, it is a rapidly moving disturbance. And those swirls or those ripples can travel to distant regions of the universe where we can try to detect them. The nature of the wave is quadrupolar, as depicted by this diagram here, this animation. It shows a ring of test masses you can imagine floating out in space away from other masses. Gravitational wave comes along normal to the plane, and it stretches space horizontally while compressing it vertically, and then half a cycle later does the opposite. That's a quadrupolar kind of a distortion that is due to the quadrupolar nature of the radiation itself. If you've taken physics 405, you may have been exposed to some of the higher order modes of radiation beyond the dipole that we're more familiar with. So dipole radiation doesn't exist in general relativity for gravitational waves. We measure the strength of a wave by the relative change in distance between the objects. So for example, in this animation, I could look at how much the distance between masses on opposite sides of the ring changed and divide that by the nominal distance between them. And I would say delta L over L, that dimensionless quantity, which is literally a spatial strain, is a measure of the strength of that wave. And in fact, we denote that quantity in the field as h of t. And the idea, if you're trying to measure this h of t, it's really the amplitude of h that tells us about astronomical objects producing the radiation. If you want to get good precision on h of t, and you have a fixed precision on delta L, the precision with which you can measure the change of distance between objects, then it pays to have a very large value of L in your denominator. It gives you a good lever arm on h. And in the case of the LIGO interferometers, L is about 4 kilometers, which gives one a delta L over L with a level of 10 to the minus 21. Actually better than that now. One other minor point is that there are two distinct polarizations of gravitational waves. What's shown in this animation is what I would call the plus polarization for obvious graphic reasons. If you rotate that pattern by 45 degrees, you get what we consider an orthogonal polarization called the cross polarization. And any arbitrary gravitational wave can be decomposed into those two components. And you don't know a priori necessarily what kind of wave you're going to get from a given source. It will, in general, be a mixture that is elliptical. So let me talk about how you detect a gravitational wave. This is an animation depicting an interferometer where this cylinder represents a laser source. The laser light comes out, it hits a beam splitter. Half the light goes this way along what we call the X arm. Half the light goes this way along what we call the Y arm. And the light travels along. In the X arm, it goes down and hits a mirror and then comes back toward the beam splitter. And likewise, along the Y arm, the light comes back. The two beams recombine. And when they recombine, the position of this beam splitter is set so that you get destructive interference going off in this direction toward your detector, the photodetector. If you look at the diagram, you can see that the crest of this Y-arm light line up with the troughs of the X-arm light, and so we get destructive interference. So one has to have a servo control system that sets the position of that beam splitter just so, and you want to keep it balanced that way. And then what happens if a gravitational wave comes along is that the gravitational wave can shrink one arm while expanding the other. And that's exactly what a microinterferometer is really good at measuring. And so you get a disturbance of this very delicate balance that you set up with a servo control system. And that causes a flickering of the light to appear at your photodiode. So that's the essence of the gravitational wave signal from one of these gravitational wave interferometers. You look for flickering of the light consistent with the signal you would expect from a gravitational wave. This is showing a little bit more detail. The laser, again, is represented here in the diagram. We have our beam splitter. We have our X arm here, a Y arm here. You'll notice that each arm has an extra mirror called what's called an input mirror. And this is the N mirror, the X arm, input for Y, and mirror for Y. The idea there is to create a Fabry-Perot cavity within each arm, basically an optical resonator, such that light goes back and forth many, many times before it returns back to the beam splitter. And if you set the distance between the mirrors to be approximately a half integer number of the laser wavelengths, then you'll automatically get that kind of a resonance. And that too requires a servo control system to set it up correctly. But the idea is that if the light bounces back and forth between these mirrors many, many times, during the time a gravitational wave is passing, then you will get a larger phase buildup difference between the X arm and the Y arm. And that'll give you a stronger signal, a brighter flickering of light at the photodetector. There's also another mirror here called the recycling mirror. As you recall, the light normally is destructively interfering as it comes toward the photodiode, but what goes back toward the laser is naturally constructively interfering. And rather than just throwing that light away, you put another mirror right there so that the light goes right back into the interferometer. And in some sense, you convert the interferometer into one grand Fabry-Perot interferometer. One other detail I should mention is that these mirrors are depicted here as pendula, hanging in this case from wires. This is initial LIGO. And the idea behind that is to isolate the mirrors from the ground. You're always trying to reduce the noise in the range, the audio range where gravitational waves are detectable on the surface of the Earth. And you want to minimize vibrations due to the ground motion. And the ground's always shaking to some degree because of waves in the ocean primarily. Okay, so let me talk a little bit about the actual observatories. One of them is in Washington State, the Eastern Washington Desert. It's actually in the Columbia River Valley. That's at Hanford. And then there's another observatory in Livingston, Louisiana. It's in a pine forest, as you can see here. These two observatories are about 3,000 kilometers apart, which means that they are 10 milliseconds away in light travel time and in gravitational wave travel time, as we would naively expect from Einstein's general relativity. And we later were able to confirm that, in fact, that is the right speed for gravitational waves. It is the speed of light. Having the observatories that far apart means that we can rule out almost every terrestrial artifact that might otherwise fool us. If we see the same signal in Washington and Louisiana within 10 milliseconds of each other, there's not much in nature that can mimic that. You know, there are some few oddball things, but for the most part, that eliminates things we might otherwise be worried about being fooled by. Having the separation between the observatories also helps in identifying where the source came from. There's going to be some time difference between the signals that arrive in Hanford and Livingston. It'll be between plus and minus 10 milliseconds. And depending on what that value is, it gives you basically a ring on the sky that's consistent with that time difference between the two arrival times. So that gives you some directionality. And then in addition, the arms of this interferometer are definitely not isotropic. They have certain preferred directions on the sky to which they're more sensitive. That's called the antenna pattern. It's very similar to what is relevant to radio wave antennas too. And you can then be favoring certain parts of the ring on the sky as being the more likely locations for the source. I'll come back to that point a bit later. We also work very closely with the Virgo Observatory. It's a European collaboration that has an interferometer in Cascina, which is not too far from Pisa, Italy. Virgo is not as sensitive as LIGO, but it's very valuable nonetheless, because if they see a signal, even if they don't see it as well as we see it, if they see it at a particular time, that gives us yet another precise timing measurement. And that improves our source triangulation, our sky localization, by about an order of magnitude, sometimes more than that. This gives you a sense of the growing global interferometer network. We have the two interferometers in LIGO in the US. We have the Virgo interferometer in Italy. There is a much less sensitive interferometer called GEO in Germany that has been around for a very long time. And their main use is that they are watching the sky all the time, or most of the time anyway, even when we're not. It's routine for LIGO and Virgo to go down for a year or so at a time in order to do an upgrade to make the detectors even more sensitive. And during those times, GEO is in what's called astro watch mode, just in case something goes off in our galaxy. that we would hate to miss, like a supernova. A brand new instrument is called Kagra in Japan. They just started taking their first data this year. They're still a long way from LIGO sensitivity, but we're hoping they're going to catch up in the next several years, or at least get close to us, so that we have at least another point on the surface of the globe that can detect the time of arrival of a signal. That gives us even better localization. One other point I wanted to make from this drawing is that we used to have two interferometers at Hanford, what we called H1 and H2. We had those in the initial LIGO days from 2001 to 2010. And the original plan was to have that same setup for advanced LIGO, which began construction in 2010 and became ready in 2015. But it was proposed by first the Australians and then later by India to host that second interferometer on the other side of the world. And in the end, we decided to go with India. There's now a LIGO India project that's it's beyond approved. It's really moving ahead. And we're hoping over the next several years that will come up online and give us yet another interferometer on yet at another location on the globe, which will improve our sky localization even more. I'll talk more in a few minutes about why it's so helpful to get better sky localization. This shows you the LIGO logos as of about 5 years ago when we made the announcement of the first discovery. Finding the Michigan Block M is like, where's Waldo? If you look closely, you should be able to spot it. Let me help you. A little circle. That's what it looked like 5 years ago. There are even more of these logos now since the discovery was made. But back when we founded the LIGO Scientific Collaboration in 1997, there weren't so many. Back in those days, you could get to know everyone in the collaboration, but it's grown about 5 times. Well, it's grown more than 5 times that amount since then. Let me show you the members of our group here. So myself, retired research scientist Dick Gustafson, who is still active and lives out near the Hanford site. 3 graduate students, Jessica, Ashish, and John. 3 undergraduates, Cameron, Grant, and Sherman. And these little letters give you some notion of the different types of work that they do, types of research they do. Here are some of the alumni from the group. The top row are the graduate students who are in their PhDs with me. Most of them have continued on in the field. And then here are, I guess, 6 undergraduates, former undergraduates, who also continued on in the field. Some of them are quite recent, you might know, like Sophie and Charlie. Okay, so let me talk about our results. So the first big result we had was back in fall of 2015, when we had our first detection. This gives you some sense of the configuration of the interferometers at that time. This diagram is similar to the ones I showed you earlier. One big difference is that our test masses are much heavier than they used to be for technical reasons. We have pretty high circulating laser powers, more than 100 kilowatts. And there's one additional mirror called the signal recycling mirror, which gives us a little bit better sensitivity to signals. These curves you see here represents the what are called the strain noise amplitude spectral densities of the 2 interferometers, Hanford H1 in red and Livingston L1 in blue. They're very similar to each other, but in those days, Hanford was a little bit better, meaning the noise was a little bit lower here at low frequencies. You'll see a consequence of that in a moment. This is a measure of sensitivity that may not be familiar to you. It's given in units of strain, which is dimensionless, per square root of a hertz. And the idea is that it's a measure of random noise in the detector. If you want to convert that to sensitivity to a particular signal of a given dimensionless strain amplitude, the rough rule of thumb to use is to take the value on the curve at whatever frequency is most relevant to your signal, the characteristic frequency of that signal, divide by the square root of the time duration of your signal, which could range from tens of milliseconds to years, depending on the type of source, and then multiply by a statistical factor that tells you how confident you are that you've seen something new that's not noise, and multiply that by a statistical trials factor that depends on how many different things you look for independent of each other. If you go through that exercise for the data that we took in the fall of 2015, you come out with a detectable amplitude for a merger of, say, two black holes of several times 10 to the minus 22. Okay. So that was the kind of sensitivity we had. And what we saw, our first signal, was stronger than that by a factor of several. So we were able to see it easily. This is our first event. We called it the golden event. And you can see that we have a squiggle in the Hanford data in red, a squiggle in the Livingston data in blue that matches up pretty well between the two. But to make them match up well, what you have to do is take the red curve, shift it by 7 milliseconds, which is within the allowed 10 millisecond window, and also flip it upside down because the Hanford Observatory, the interferometer, is rotated 90 degrees with respect to the Livingston Observatory. So this is almost raw data that we're looking at. These two things happen more or less at the same time, and they look very similar to each other. Down here is a pair of spectrograms. So these are indicating the intensity of the signal as a function of time horizontally and frequency vertically. And so you get this characteristic pattern when two black holes or two neutron stars come together, in which the frequency and the amplitude of the signal both rise together. You get a chirp. And you can see that the signal is stronger in the Hanford data than in the Livingston data, and that's because the Hanford data was more sensitive at the lowest frequencies where the signal was strongest. So this is the data up in the top in the time series. This is a spectrogram version. What's shown in this row is basically a fit to semi-analytical waveforms that are based on general relativity, along with predictions from exact numerical relativity waveforms for the closest set of parameters for the masses. And you can see there's very, very good agreement between what we see in the data and what you would predict from general relativity. So this was called the golden event. We now call it the first golden event because I'm going to show you another one. These are some of the parameters for that first detection. We have one black hole with 36 solar masses with some significant errors on those. Secondary, a lighter companion at 29 solar masses. The final black hole, which they merged to form, had a total mass of 62 solar masses. The black hole spin is a measure of the angular momentum divided by the maximum allowed for a black hole of that mass by general relativity. It's pretty high. You expect it to be around 70%, and what was inferred was 67%. The luminosity distance, the distance to which it appears to be, was about 400 megaparsecs, about 1.3 billion light years away, and it had a significant redshift of 0.09. Now, you might be bothered by these three numbers because 36 plus 29 is not equal to 62. And the reason for that discrepancy, and it's really just a calculated discrepancy based on what we understand from general relativity, is that we lost, or that system lost, about 3 solar masses of energy within a couple of tenths of a second, implying that there was an enormous amount of invisible luminosity in gravitational waves at the level of almost 4 times 10 to the 56 ergs per second, which means it was shining more brightly in gravitational waves at that moment than the entire rest of the universe was in ordinary electromagnetic radiation. So Stephen Hawking is famous for many things. One of the things he's famous for is for his statement that black holes have no hair, by which he means that black holes can be characterized by basically their mass, their angular momentum, and if they have any significant electric charge, by that amount of charge. And that's pretty much all you need to know. It's all you can know about a black hole. So here we have an event involving 2 black holes coming together in a very strong gravity realm. And you might wonder if we can test that claim. And the answer is that yes, we can test it. To give you some sense of how you do that test, it's helpful to realize that there are 3 distinct phases in the merger of 2 black holes. We have the in spiral phase, where you have 2 black holes that are clearly distinct from each other, going around and around, but getting closer and closer because they keep losing energy to gravitational radiation. And as the system loses energy, the orbit has to shrink. Then you have the merger stage, which gives you the maximum amplitude when the two stars come together. And then you have, after that, a ring down in which the excess angular momentum of the star is in some sense shaken off to make it form something that is consistent with a pure black hole. And so you have these three distinct phases, and you can try comparing the parameters of the system that you infer from these different phases and seeing how consistent they are. This is another representation of the calculated waveform that best agrees with the data in comparing with numerical relativity. Again, there's just beautiful agreement indicating that general relativity is predicting the system very, very well. To give you, again, a sense of the dynamics of the system, we have here a curve with the y-axis on the left showing you the y-axis on the right, showing you the separation between the two black holes in units of the Schwarzschild radius of the final black hole. And you can see it comes to an end just above 1, just before the two merge together. And then on this green curve, which has the y-axis on the left, we have the relative velocity, relative speed between the two black holes in units of the speed of light. And you can see that just before they merge, the relative speed is getting up close to 60% of the speed of light. And each one of these stars is roughly 30 solar masses. So it's an incredibly violent process. I guess I've already said all of those things. But the basic bottom line of this graph is that black holes do not have long, scraggly hair. We can't rule out a crew cut. We need more precise measurements with more events to say something very definitive, very highly sensitive. But this first test of the statement that black holes have no hair was passed with flying colors. There's no evidence here that the black holes are behaving differently from how general relativity would predict them to behave. That first run we had in fall of 2015 gave us 2 5 sigma detections, the one I've already shown you, plus another one which we call the Boxing Day event because it came the day after Christmas. The event names are 150914 and 151226, named after the dates when they were detected. This signal was not as strong. The spectrogram doesn't really jump out at you, and it's almost impossible to see a signal in the time series just by eye. But nonetheless, this was strong enough that we were very confident to claim a detection. We were happy, though, that our very first detection was this guy, because he just jumps out at you. Okay, so we had another run called the O2 run that began in November 2016 and went through August 2017. And we had a number of nice detections from that event. Here was one in January of 2017. Here's one from June of 2017. And here's one from August of 2017. And you'll see that there are now 3 spectrograms in 3 time series. That's because in this run, and only in the last month of that run, in August 2017, we were joined by the Virgo interferometer. Now, as I said, the Virgo interferometer is not as sensitive as LIGO, yet they are able to detect strong signals to some degree. And you can see that here. Here we have a really bright signal. It's actually brighter in the Livingston interferometer than in Hanford because in this data run, Livingston had better sensitivity than Hanford. And you can see it in the Virgo data too, not nearly as strongly, but strongly enough that it gives you a sense of where that signal came from. Let me illustrate that. This blue banana on the sky is the part of that ring on the sky I talked about earlier, where the antenna patterns of Hanford and Livingston favor a signal coming from. So if you said, where does the signal most likely come from? It's somewhere on this banana. That's a pretty big banana if you're trying to find the source with a telescope, ordinary optical telescope, say. Bringing Virgo into it, however, brings the size of localization implied by the 3 detections down to something that initially was the orange ellipse, and then with refined analysis became this little green blob. And so that means that if you're trying to find this signal on the sky, find something electromagnetic associated with it, you're in much better shape if you have the Virgo interferometer helping you. Now, you might wonder, why would you even look for something in the aftermath of two black holes merging together to form a third black hole? That's a good question. Naively, you wouldn't expect to see anything, but you never know. You want to keep your mind open. And in fact, there was an event last year where at least one group claims to have seen something in the aftermath of a black hole merger. But the real interest in this is not so much being able to follow up on binary black hole mergers, it's being able to follow up on a completely different kind of event, namely one involving neutron stars. And that brings us to our second golden event. This one was taken in that same run, just 3 days after the one I just showed you on August 17th, 2017. And it shows you the spectrograms from Hanford, Livingston, and Virgo. Notice that we're looking here at 30 seconds of time, not a fraction of a second. So these are very long-lived signals. This is what you expect from a binary neutron star merger. Much lighter masses, about roughly 1.4 solar masses each nominally for a neutron star. And so that creates a much longer signal in the detector. This is also known as GRB 170817A because a gamma ray burst was seen almost simultaneously with this signal. And it's also known as SSS17A and AT2017 GFO because optical telescopes also saw something associated with this event. Before I get to that, let me talk a little bit more about the gravitational wave signal. Let me, in fact, play for you, and I don't know how well this is going to come through your computer, from my computer, but let me play for you what the event sounded like, including the noise. And you can try to detect when the signal happens. And you will have the advantage, if you keep your eyes open, of following where we are on this little trace to know when to expect the signal. If you want to challenge yourself, you can close your eyes and not get that benefit. Unless you have a computer with a good woofer attached, you probably can't hear anything right now that sounds like a signal. Okay, I don't know if you heard that or not. I can hear it. I've become familiar with that sound. You would not want to count on someone sitting in the control room detecting that live, although you could do that in principle because this is in the audio band. You can literally plug your data channel right into a speaker and listen to it. And sometimes that is done in the control room. But you can imagine it'd be pretty easy to miss that little signal. Let me play for you the pure signal reconstructed from the data without the noise, and you get a sense of what the underlying signal sounds like, the chirpy behavior. And again, unless you have a woofer, you're probably not going to hear the signal, even when the noise is removed at this frequency. Okay, so if I were giving this lecture live, I would bring a woofer. You could hear that thing all the way through. Okay, so I mentioned that there was a gamma ray burst associated with this event. Let me play for you the spectrogram, but only the last 6 seconds of it or so, and also show you a depiction of data from the Fermi Gamma Ray satellite. There's a chirp, and there's a signal on the Gamma Ray satellite, about 1.7 seconds later. So these are signals that traveled over 40 million parsecs, well over 100 million years. And they got here within 1.7 seconds of each other. Now, we don't know exactly how long after the merger you might expect a gamma ray signal to be sent out. It's a very complicated process to produce those gamma rays, and I'll show you a rendering of that in a moment. But if you assume they were sent out at the same time, you could say, well, the fact that we see a 1.7 second delay means that light takes a little bit longer than gravitational waves to get here. Or you could say, well, we think the gamma rays are actually emitted 10 seconds after the merger, and yet they caught up a good bit. And so with those kinds of extremes, you can set a limit on the difference between the speed of light and the speed of gravity. If you go through that exercise, you get the results, basically down at the level of 10 to the minus 15 or so for the relative difference between those speeds. So our assumption all along that there will be a 10 millisecond delay between Hanford and Livingston for gravitational waves turned out to be very well founded. Let me play for you an animation from NASA of this neutron star merger and the aftermath. It's a NASA production, so it's fancy. So we have two neutron stars coming together. Bang. They come together, they merge. Most of the stars go into a black hole pretty quickly, but they also emit radiation and matter along basically the orbital spin axis of the system. And you can also see gravitational waves being depicted here. The gamma rays that we're seeing presumably came from this jet that you're seeing out here, but notice there's also some material around the center. Let me continue the animation. All this material here is also quite interesting. Aside from the initial gamma ray signal from the jet, there is going to be an electromagnetic aftermath from the stuff that stayed closer to the original merger point. Okay, so at that time, we had an agreement with about 70 different observatories on the Earth and in orbit, and just all over the globe, including a detector in Antarctica, in which we would tell them if we saw something interesting that might come from a black hole merger or a binary neutron star merger or a supernova. And so we would tell them where we thought it was in the sky, and then they would go look for it as best they could with their various types of telescopes all over the electromagnetic band. And so there are quite a number of them ready to point when we gave them the signal. So as you might recall from the spectrograms I showed you earlier, in fact, I guess I forgot to point it out. Let me just show that to you explicitly. Hanford has a pretty decent signal. Livingston has this absolutely beautiful signal. You can see all the way through here. And Virgo has nothing. Virgo was on and operating. It saw nothing. Now, I told you that Virgo is less sensitive than Hanford and Livingston, but you'd think it would have seen something. So you might wonder how we could do triangulation if Virgo didn't see it. Well, the answer is that the fact that Virgo didn't see it is like the dog in the Sherlock Holmes story that didn't bark in the night. That information was actually critical. What that told us was that the point on the ring defined by Hanford and Livingston, shown by these two blue bananas, those are the two favored locations from the LIGO data alone. Somewhere on those points, there had to be a location where Virgo was not sensitive. It was in what's called the node of the antenna pattern of Virgo, and that tells you to look right there. And so that's the information we sent out to the electromagnetic astronomers within hours of the event. We said, look here, you might see something. And they did look. There were quite a number of them who were looking at that time. This shows you a whole animation of the world globe turning. And different astronomers had to wait their turn to look for this signal. Unfortunately, the source was relatively close to the sun. And so basically an optical telescope had to wait until sunset, and it had only about an hour's worth of observing time between that sunset and when the source went over the horizon. So it made it pretty difficult. And the first groups that could have seen it in principle were in Africa, but unfortunately the seeing conditions that night were not very good in Africa, and they just didn't see it. So it had to wait about 10 hours for it to be visible in Chile. And 6 different optical telescopes did see it in Chile. And once they announced the location of that event, the location of the optical source, that allowed everyone else in the world to know precisely where to train their telescopes. In fact, one of the groups has a University of Michigan contribution, the Dark Energy Survey, the dark energy camera. So if you were in Australia, it was pretty frustrating because you had to wait and wait and wait before the signal became visible, and you knew there was something to look at, but you had to wait. That's just the way it is sometimes in astronomy. So this is a summary of some of the observations taken that first day and then many days afterward. This shows you the gravitational wave spectrogram I showed you earlier. These are the time series of gamma rays from the Fermi satellite that I showed you earlier, plus another satellite called Integral that also saw gamma rays at the right time. This signal was seen in gravitational waves, gamma rays, eventually in X-rays. It was seen in ultraviolet, a lot of observations in the optical, pretty good number of observations in the infrared, and also some observations in the radio eventually that showed up. And we put together a so-called letter that had 3,000 authors and 70 collaborations that summarize all these different results in what we call multi-messenger observations of a binary neutron star merger. One of the highlights of this whole campaign of observations was the observation that the spectrum seen optically changed dramatically, or at least I should say invisible light changed dramatically over the course of the first week. Initially, the spectrum peaked here at about 4,000 angstroms in the UV, but within a week, the peak had shifted way over into the infrared. And that was actually something that had been predicted by theorists as to what should happen in the aftermath of a binary neutron star merger as evidence for what's known as a kilonova, in which you produce lots and lots of very heavy elements like gold, silver, platinum, and uranium. In fact, the theory at that time, and now it seems to have been bolstered considerably by this event, is the idea that most of the very heavy elements in the universe have been produced in this kind of a process, as opposed to, say, a supernova. All the supernova simulations have been done over the years have confirmed that one can produce lighter elements, but it's very difficult in those simulations to produce the very heavy elements that require lots and lots of neutrons. And one thing that neutron stars have a lot of, especially in the aftermath of a merger, is a lot of neutrons floating around close to each other. And there's enough there that you have this R process that leads to these very heavy elements. In fact, there's so much gold produced in this event and so much publicity that even Business Insider learned about this and featured it. They probably had in mind something like this, but they may not have appreciated that it's a long way away to the source. 130 million light years makes it difficult to harvest that gold. There were a number of estimates at the time as to how much gold and platinum was produced. One estimate was an amount of gold greater than the weight of the Earth, which sounds like an awful lot, but that was actually a conservative estimate compared to others. Here's tens of times the mass of the Earth in gold and platinum. Here's someone estimated the monetary value of all that gold. Here's someone who came up with 200 Earth masses of gold and 500 Earth's worth of platinum. And I have no idea which of those estimates is best grounded, but a lot of heavy elements were produced. If someone comes to you with a proposal for an interstellar expedition to harvest some of this precious metal, I would be careful. Okay, so those are somewhat old results. I wanted to go through them because they're famous and they're neat to talk about. But let me also talk about some of the new results. We relatively recently completed a run called the O3 run between April 2019 and March of last year. It was supposed to be a one-year run, but the pandemic cut it short a little bit. We had more sensitive detectors than before, both for LIGO and Virgo. And what we were expecting to see were dozens of black hole mergers, a few neutron star mergers, and perhaps a surprise or two. So what have we actually seen? Well, we've seen dozens of black hole mergers. We've seen at least one neutron star merger, and there have been some surprises. This shows you a graph showing you the cumulative number of events seen in the first run, O1, then O2, and then you can see that the slope changes dramatically in the O3 run. So we're seeing many more events per week in the O3 run than we did in the earlier runs. This is one of our more intriguing events. This is a binary black hole merger called 1904-12 because it was detected on April 12th, not long after we started running. And what's unusual about this particular event is that the masses of the two black holes were distinctly different from each other. Prior to this event, all of the mergers we had seen had been more or less compatible with equal masses. You know, there was some error on each one, but you couldn't rule out equal masses for the two stars. And that gives you some sense of how they might have been formed as a binary system. If they're formed together in a stellar nursery, you might expect them to typically have similar kinds of masses, whereas if they came together randomly, say in the core of a globular cluster, then you would not expect them necessarily to have the same masses. So that was unusual about this particular event, distinctly unequal masses. And we were really excited about that until we saw this event, which had even more unequal masses. Here we have almost a factor of 10 difference between the masses, 23 versus 2.6 solar masses. And of course, one of these masses is quite light. In fact, you might be surprised to see a black hole with a mass like that. It was well localized, had a very high signal to noise ratio, so we're able to see where it might be on the sky, but no electromagnetic counterpart was seen. And so that's also a potential clue as to the nature of this event. 2.6 solar masses is really light for a black hole, but it's pretty heavy for a neutron star. This shows you a contour map of one mass versus the other, and it shows you that there's some spread in the allowed values of these masses based on reconstruction. But nonetheless, this is a pretty heavy mass for a conventional neutron star, and it's extremely light for a black hole. It falls into what's called the low mass gap, and so it challenges ordinary stellar formation models of how you form black holes or neutron stars. So it's a little bit of a mystery, and that's why we have this graphic showing this big, heavy black hole over here and something over here that may be a neutron star, or it may be an even smaller, more compact black hole. We just don't know. Our data just aren't precise enough to allow us to see anything. We do not see any evidence of any kind of a tidal deformation indicating a neutron star. What we see is perfectly consistent with two black holes that behave more or less like point masses. Here's another interesting event that was a surprise. This was taken on May 21st of 2019. And if you look at these spectrograms, it's quite bright in Hanford and Livingston data. The top frequency is relatively low. It's only about 65 hertz at the point of merger. That automatically tells you that this must be a massive system, one where the two black holes come together very quickly before they can go around each other too many times. It's a short, strong signal. It peaks at low frequencies, meaning it is a massive system. How massive? Well, this shows you the same kind of a contour plot of one mass versus the other. And you can see that we're looking at kind of 85 for one of them and 66 for the other. There are large errors on these, but these are heavy black holes. And that's surprising, not just because they're heavy, but because they both fall into what's called the high mass gap, which is expected from something called pulsational pair instability. There's a region of stellar mass in which you would not expect a black hole to form, because if it's much, much heavier, then it forms okay. But if it's in this intermediate range, then the star creates gamma rays that blow off the outside of the stellar envelope. So you tend to systematically lose mass if you're in a certain range, and yet here we have two stars in that range. And so that's potentially evidence of what's known as a hierarchical merger. It could be that these two black holes did not form from each one did not form from a single giant star in the past. It could be that each one of those was actually formed from the merger of prior black holes. And that's actually a theory that's getting quite a bit of attention right now. One other thing to note here is that the total mass, when you bring these two black holes together, is about 150 solar masses. And that makes this the first detection of an intermediate mass black hole, which is defined to be a black hole greater than 100 solar masses, but much lighter than the sort of things you find at the centers of galaxies. So here's a summary of all of the black hole and neutron star measurements we've published to date. This is not the complete O3 set. We still are looking at the second half of our data, but you can see we've already got about 50 different detections. The vertical scale here shows you the masses of these systems in solar masses. So you have two black holes coming together to form a third black hole, or you have two neutron stars coming together to form what we assume will be a final black hole. Down here are electromagnetic measurements of neutron stars, basically pulsars in our own galaxy, for which you can measure the mass pretty precisely if they're in binary systems. These purple measurements are electromagnetic measurements of black holes in our galaxy based on systems that have some relatively ordinary star going around them, and there's an accretion disk around the black hole, and you infer that it's a black hole, and you infer its mass from the binary properties that you can measure. So you can see that the LIGO masses tend to be quite a bit heavier than what we see in our own galaxy. And you might wonder if that means that we're seeing a different population of black holes. That's not yet clear. It could just be a selection effect because LIGO sees heavier objects much more easily than lighter objects because the amplitude of the signal is proportional roughly to the mass of the system. And so that means that you can see farther out in the universe if a system is heavier. And since the volume of the universe scales like the cube of the distance to which you can see, you have a tendency to see heavier systems farther away. And so that could account for most of the difference between the masses you see up here and the masses that are seen in our own galaxy. We do, after all, see some masses in this range. Okay, so actually, how am I doing on time? I haven't been paying close attention to it. Running late. So tell you what, I'm going to skip the rest of these slides, and then if there are questions, I'll come back and address them. So in summary, we've observed merger of stellar mass black holes, 48 definitive discoveries published. Virgo has now detected gravitational waves too. That has dramatically improved our triangulation of sources. That has made electromagnetic follow-up feasible. We've had 2 discoveries of binary neutron star mergers, and the follow-up campaign on one of those was stunningly successful, confirming the kilonova hypothesis. Signals were seen in gamma rays, X-rays, ultraviolet, optical, infrared, and radio. I already said that. And then we are starting to see in our latest run unusual binary black hole systems that challenge conventional models. We have asymmetric masses, we have an object in the lower mass gap, and we have perhaps 2 objects in the higher mass gap. And we've also seen the formation of an intermediate mass black hole. So there's more to come. Lots of good science to do, both in the data that we have in hand that we haven't finished analyzing, and more excitingly, what we're going to see in the future with even more sensitive data. So the dawn of gravitational wave astronomy is here. We're actually well beyond the dawn now. The next 20 years should be eye-opening, and the next century could be eye-popping. We'll see what we find. Thank you.